through the TCP sockets, and then from there on we create the CSV file on an SD card, a local data storage, and we put it into a JSON string and MQTT to a broker. So here you can see all the levels from acquiring the data up to the cloud and to the local data that you can then read out, for example, through Wi-Fi. So now we have the 3 energy sensors. This is now a little bit a glimpse into the future. They all have, except for the gas flow meter, a CAN interface and a Bluetooth interface. And our vision is to provide a data API to you so that you can interface with these sensors that are calibrated and also used for the official measurements. And read into your own telemetry system onboard computer based, for example, on an ESP32 or a smartphone or even a combination of it, so that you have your low-level kind of data or sensor node and then connect it to the cloud Node-RED or whatever you use. And this is then very similar to the architecture that we have been using the last 10 years. So are there any questions on this first level so far? Creating a telemetry system is not an easy task. It's also a lot of noises in the engine compartment, I tell you. EMI is a problem via vibration, heat. So you have to be careful that you protect your electronics and make sure it's kind of in a Faraday cage. Yeah. So this is, if in the upcoming webcasts or bootcamps, maybe we go deeper into this technology, because I want to know actually what can you build yourself and where do you need know-how from us. Okay, then let's move a level higher. Some low-hanging fruits in data analytics. Let's say you have this data stream, several data points, in this case like GPS data. Of course, then you can connect all the dots and you get, like in this case, the Mandalika racetrack from Lombok. Then you can overlay speed and you can overlay energy use. So now we have just time series or time-based or distance-based data. And what happens if we aggregate these data and get to burn and coast patterns? So where you can see really where your driver was hitting the throttle on the track and where. Then we can even zoom into this S-curve here. And instead of energy use, we overlay speed, because we have already speed information in our data, and we can actually really see the speed profile that your driver used when he did this S-curve. So the question was, did it according to your, would say, speed program or the speed profile that you were using in your data strategy? So you see here, you can close the loop. You tell your driver to go in with 40 kilometers per hour and then take this one with maybe 30 kilometers per hour, but here we can actually see what speed he did this S-curve with. Now, this is telemetry data, the raw data that we got out of our OBC. You can see you can have several levels. First you get the raw data, and then you need to aggregate. And I'll show you one example to improve the quality of your data and to add new dimensions, as I could say. So here we have, now let's say you go out on the track, you go around, you make many laps, and all your computers see this data coming in at certain time intervals, right? So we have lap 1, 2, 3, 4, lap 1, 2, 3, 4, start time, end time. And that's it. This is the data chunk that we get when we kind of complete the attempt and come back to the finish line. The problem is, with time-based data, you cannot do much in motorsports, because you want to know where the magic happens. Where did he hit the throttle? Where did he change his speed? Not when, right? And you can use a little trick here. It's the Haversine formula, where you can use actually the data points that we gather in GPS and then calculate the distances between the data points. And so you get actually to distance-based data. formula that you can, there are algorithms around, and when you follow the link from the link I gave you, you can scroll down and there is actually a Python code including exactly this algorithm that I show you now. So now that we have our chunk of data, like 1, 2, 3, 4, 5, it's all in one thread. We need to have like a lab-based data. I want to see the data from lab 1, 2, 3, 4, right? So the trick is to add the GPS data of the start line and the lap line. So when your driver crosses the start line, we know now he is on track. And then when every time he crosses the lap line, we know one lap is done and the next lap begins. This is how we can segregate actually this chunk of data and have for every lap its own data set. Lap 1, 2, 3, 4, and as you can see, now different colors. And this is now at the level where you can start comparing the different laps and how your driver did in the different laps. So the trick is actually, on the low level, a line-line intersection algorithm. Also very easy if you have your data stream, you can reuse this code that we provide to you and just use it on your data and you get your laps in different segments. So this is again the QR code for those who are new now. This QR code brings you to a website that includes all the resources from today's bootcamp, computer code, the presentation, link to sandboxes. So now, what did we do? We had our chunks of data like 1, 2, 3, 4, 5 on a time basis, and this is what we have now. We have all the labs in a different data set and distance-based. So this is now something that you can use in motorsport. You can use it, for example, to do data correlation. Like here you see we have the, from the joule meter maybe, the instantaneous, either the energy flow, the electrical flow, or the liquid flow meter in the gasoline world. Every time it hits the throttle, we see a peak. And when it comes to the cumulative energy consumption, every peak generates a step. So step up, 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 up. So the longer we are on the track, the higher is the energy use. And you can see the correlations between the two. And of course, every time you hit the throttle, your speed goes up. What you can see here on this track, this was actually some data that Ian was creating for us, because I told him, when you do, here you see speed goes to 0, so this is actually half, a right half in the middle of the track where you have the mandatory stop. So speed goes to 0. And I was telling him, if you do your burn and coast, don't do it consistently. Just play around a little bit, just do with no intention. And in the second one, try to be as precise as possible. Try to remember when, at what point did you hit the throttle, and at what point did you coast, until what speed, and then to regain speed again. So you can see here, we have no consistency, and here we do have consistency, and you can also see, I see it on the next page, if you have inconsistent speed profile like this, so your driver was not able to reproduce the strategy on track, you will have the same in the energy use. So there is a correlation between the two. If, say, your speed profile is very precise, here you can see 3 laps. So will be your energy use. Why I tell you this? It's not only about data. It's also about what is your driver doing with the data. If you cannot have a certain consistency and be precise on the track, data is actually useless. So if you come up with a new strategy and you are able to apply it on track exactly as the strategy should be, then you are on this level. So this is really much depends on how your driver can apply, I would say, a planned speed profile on the track. And then of course you can do quantitative analysis. Here we can see the energy use of several labs. So the first we identify the best and the worst. So this is the best and the worst. You can see a difference of 14%. Same driver, same vehicle, different race behavior. And now comes the why. Why is the red one better than the blue? So what would you look at now? Where did he hit the throttle? And for how long? We can see that the red one, the red profile, is actually better than the blue ones because we have a shorter, I would say, impulse here, you know. And finally, it's the area of the impulse that counts. And then, when you kind of overlay this information with GPS data, we have seen it in the burst and coast map, you really can see what is the difference between the two strategies, between lap 5 and 6. Lap 5 and 6. You see now how it all comes together in a very simple way by just looking the right way at data. Because this is something a driver and you can understand very well. Is it according to the race strategy that you formulated or not? Or you can even, at that point, use a very, I would say, tricky process to get just through data, to get in an iterative way to learn from the data and get better and better without even using modeling of the car or modeling of the racetrack. It's called MVP, Minimum Viable Product. Who has heard of Minimum Viable Product? Is this something that you all know? Okay. MVP is not about products. MVP is about learning from an idea. Is an idea worthwhile? Is the idea correct? So we validate an idea. Let's say we have an idea of a new race strategy. So what we do is, like we come here to Lucelle track, we implement 3 race strategies, maybe 3 different ones, an aggressive one, a very efficient one. So with these 3 strategies, your driver goes out in the practice runs or in the mileage challenge, and we create data. So we measure the strategy right on track with telemetry. We come back with telemetry data and we learn from it. And now the next step is very important in MVP. You look at the data and you say, is it good enough to continue? Or is it so bad that we have to pivot? Pivot means change the strategy completely or refine it. This is when you continue. So this means, like in this case, we had the driver applied 3 strategies. In lap 1, strategy 1, then he crossed the lap line, then he applied strategy 2, and then strategy 3. And which do you guess is the best? It's obvious. Yeah. It's strategy 3. From a quantitative point of view, because data does not lie. And here you can see back in the pattern of burn and coast, why is strategy 3 better? So this means you can skip this pattern here and ask your driver to follow this one and maybe improve here and there and refine it, make it better and better with every lap that you do. You don't have to know anything about physics at this point. Just look at the data. This is why I call it the low-hanging fruits, and you can even go further. You look at how did your driver in the corners. So you zoom into this S-curve, and you can see here maybe you have 3 drivers or 2 drivers. They take the corners completely differently, and you can go back again to the quantitative analysis and say, what is the energy efficiency here, here, and there, and what are you doing? You choose the one that achieves the best quantitative result. That's it. Same with driving dynamics. We have 3 different race lines and 3 different race burn coast patterns. And this gives you a lot of information how to take this S-curve. Data as a storyteller. What we have done here, you can imagine you have now maybe an attempt, 4 laps, and we have put all this data into a scatter plot. So we don't distinguish between from lab to lab, we just look at the data and the pattern that the data creates. So we have here the acceleration, 0. So we accelerate, we decelerate, this could also mean brake, right, braking. And we have GPS speed. When you see this pattern, what can you see? Let's say I give you the origin here, we start from here, this is the start line. You accelerate up to your target speed. Now we are at 40. This was maybe the straight line that we have at the start line, after the start line. Then you coast, and you burn again, you coast, you burn, you coast, and then go back to the start line, you go to 0 or to the speed of 0 kilometers per hour. What's this here? Negative accelerations. Braking. Your driver hit the brake. And you told him not to do that in Shell Marathon. You see what the data is telling you? It's telling you the truth. So you can see really patterns in this in this whole data chunk by knowing how to present the data. And now I show you something that I think is really interesting. Here we can see we started from maybe 45 kilometers per hour, and we see this huge blob here. So obviously we go down with minus 0.9 meter per second in square. This could be halfway the one where we have to do the mandatory stop. If you know exactly these characteristics of your vehicle, the rolling resistance, everything is inside this data here. So you know exactly at what point you can start to coast until your vehicle comes to a complete stop midway of the racetrack without even hitting the brake. This is all in the data. And you don't have to know any formula of traditional physics to do that. Just what you have to do is to come up with a strategy, define a profile that you think is best, and then, this is the key point, your driver applies this strategy very, very precisely and reproducibly on the racetrack. And this is your win. There is actually some Python code. This, again, pure code brings you to the website. I show you where it is. So this QR code brings you to this website. This is some blah, 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 blah. Then the bootcamp structure. This is where we are now. We are in the level hall 2, and we almost used half an hour. This link now brings you to a sandbox. You can download the sandbox. It actually creates a Python environment in your browser, and you can play around with the data, with all the algorithms I just have shown you. Explore what you can do with basic data analytics. You don't even need an Anaconda environment. So all you have to do is to click here, and then it opens up an environment for you. We use the same environment later for the interesting stuff with AI and knowledge graphs. So it's the same environment you know from Anaconda. Can restart the kernel, go through all the cells, execute them one by one. So I want to go a step further, go to the next level, live data. Live data is when you send data direct from the racetrack to an IoT server. That's what we have done with the telemetry in the last couple of years. So we have this information that we gather in the Oppo computer here, create a JSON string, load it up to MQTT. And this is how we used it. We used it in the championships. You can see the urban concepts, the best ones lining up and doing a head-to-head race against each other. And you can see the live data here, the position and also how much energy they use. This is how we use live data, and this is where also we would like to share our knowledge with you how to do that. I mean, you guys know MQTT, but maybe there's always some, how can you do it industrial grade, how can you do it reliably? When kind of you disconnect, what happens then if you lose your connection? This is everything that we have also experienced and had many fuck-ups in the last couple of years and had to solve them. And then finally the data flow is like this. We have our race car, we connect to an MQTT broker. All this happens, in our case, happened on an Azure cloud. You can also use Node-RED or Grafana. Both are reliable. We have seen all of these in the off-track award submission. And then we have kind of a kinetic service that does some data cleaning, and then we kind of store data locally in a database, or we have used it as monitoring on your tablet to see how it works, or as we have seen before, on a live. LoRa is for long range, but also limited transmission rates. We have used 4G, but LoRa is possible, but you will have limitations in the amount of data you transmit from the vehicle to the server. Systems modeling. So this is now the next level, where you go a step further from the data and look how your vehicle works in an environment like a track. So you can start with the track data. I've seen that in many off-track award submissions you use Google Maps to extract data from the racetrack, maybe without knowing that through this QR code you get to the telemetry wiki, and you receive the track coordinates actually from Shell. They give you the track coordinates like the Lusail track. That includes also the elevation. There's no much work than download this CSV file and use it in your modeling environment. So using the racetrack as a model. And then of course we have the different scenarios we already addressed. We have this driving the straights, the typical formula from good old Newton that we all know. The more mass, the more force. We have the slopes, where the gradient comes into the picture, are also here. Is everything covered in the textbooks? You don't have to dig into this right now. Taking the corners is also very well covered by many articles. What is the speed when you enter a corner? What is the exit speed? So the idea is to never ever hit the brake. So be sure to have always the right speed when you enter a corner, and you know also about the coefficient of friction and the centroid, and all that stuff comes into play at this moment. Taking the corners is a holy grail in racing. So here's where you finally model the car. You have finally kind of a total force that you have to overcome to move your vehicle from one location to the next. And then finally, you can really go down to your powertrain, like in this case, the electromotor. So we know to overcome a total force, we have to apply a torque. To overcome a speed, or to move from one spot to the next, we have a rotation speed that our wheels have to apply on the road, so to put the PS on the road. So finally, the torque again depends on the current. The current that goes through all the wires, and the speed is dependent on the voltage. So this means your electromotor has to apply the current and the voltage to overcome this force. And this finally leads to the power and of course the energy integrated over time. This is what your motor has to deliver. So when we look at data modeling, we see that our strategy that started very easily, you can remember the first strategy we looked at the beginning, we see there's a lot more that we have to include now on the data side. But the good news is it's not all dynamic data. We have also a lot of static data, like the car mass. Everything what you see here is covered in the textbooks. I don't want to spend too much time on it. I want to go into holistic racing. See the time? We have 20 minutes left, yeah? Holistic racing means we have to solve a problem that is, first of all, a multi-objective problem, where goals fight against each other, and it is really difficult to formulate in a way where you get to a global optimum. Local optimums is easy, but the global optimum from start to finish line. What are conflicting goals? To put it bluntly, this is a conflicting goal. You want one on the left and you want this also on the right. So what are you doing? Multi-goals in industry is if you have to develop a product that has a high quality, costs no money, and is delivered tomorrow. You see the problem here. This is a conflicting goal as well. We call it the magic triangle in engineering. What do you think are the conflicting goals in Shell Eco Marathon? It's a low energy use, short lap times. To have short lap times, you want to speed up. When you speed up, you use energy. Your safety could be become a matter if you're too fast. You see, these goals, they really fight against each other. Now let's see how we could formulate it in a mathematical way and solve it differently, maybe, as you know, from traditional problem solving. That's where the Pareto front comes into the picture. I've seen in one submission of yours using the Pareto front. The Pareto front, we have now, let's say, we span an area of lap time. Short lap time here, long lap times here. Low energy use here, high energy use here. So now let's think we have these two, we have energy use, we have lap times. Imagine this in a formula that somehow produces a result. And we want to have what we call a solution space. So if you have any value that this variable can take, we'll end in a solution space like this. This is a hypothesis, just a model for your brain. Let's say all the results are in this oval shape. Now let's go a step further and say, what if you want to have everything at a minimum? Minimum lap times, minimum energy use. So everything minimum means it goes to the left here, it goes down here. So you end up in an area where you say, this is the Pareto front. This is where you want your vehicle to be operated. So again, imagine you have a kind of a knob in your vehicle that says, I can put it to speed. I can make the behavior of a vehicle very fast responsive. I can put it to eco, then it becomes very energy efficient. Or it becomes something in the middle. If you want your vehicle to be very fast, where would you be on that Pareto curve here? Here? Here, yes. This would be your fastest possible driving state. In mathematical terms, we say the weight is 1.0, normalized. The weight on the energy is 0. We don't care about energy at this point, we care about speed. On the other hand, when we want to have the maximum possible energy efficiency, where it is? Where is it? Here.
Bottom.
Yeah. So we have no weight on speed, but we have 100% weight on the energy use, or something in between. That's the magic of approaching a multi-objective problem, and I'll show you later how we can formulate it in a data science way to find a global optimum. This is a real result from a team that did 11 labs, and so what they did is they gradually went from optimum times to optimum energy results and created their own specific Pareto curve for their specific vehicle. And you can see here what you can read from this graph. You can see that with a little bit of sacrificing lap time, we get a huge energy saver. It's not much in time, but almost more than the half in energy use. And the same happens with the lap time. Just a little bit of sacrificing energy use, you get a huge difference in lap time. And I think we all agree that operating our vehicle in this area is probably pretty good. So see, this is another powerful information that you receive from your data. Knowing where to operate your vehicle. So, how do we solve it? Differential equation systems, covering all the straights, the curves, the crests, the corners, minimum energy, minimum lap time, safety at all times. I tried. I gave up after 2 weeks, and I was looking for a different way to do that. Dynamic programming and genetic programming is something that comes very close to solve problems like this. They are made for solving complex problems. But there is a third way. But first I want to show you the map how to solve complex problems. So we have many different options. If you want to do a global approach, we have seen here genetic programming is one possibility. I want to show you how we use graph-based programming using data science possibilities like the Dijkstra, like the A-star. This is something that is very new now in our data-driven world. So don't forget traditional physics completely. We can see how we can the physics will be reborn in modern data science. And a knowledge graph is actually how you describe a problem with nodes and edges. In the nodes are the things in our world, and the edges are the relation between the things. So here you see a couple that loves each other, has a car, and you see everything that's happening in this couple in the semantics. This is in the edges. The edges are the ones that are important. It's interesting that Nala, the female in this couple, she is part of a huge worldwide network that is constantly changing, like a social network. So you can see a graph can scale from something that is very small to something that is huge and covering the whole world. And this is something that where we need special algorithms to use. You can forget the traditional algorithms, they will not be fast enough. They are called graph transformers, and they are specifically designed for graph-based algorithms. That is also, as we see soon, the fabric of our modern AI. So we have pathfinders, we have community transformers that you use in TikTok or LinkedIn, or we have meaning transformers, like a PageRank, and this is something you use every day without knowing it. Do you have a clue?
ChatGPT.
Google, yeah? You can imagine Google without these powerful tools would not be that fast and precise as it is today. So we have the PageRank that is exactly, everything is written in matrices, and you have matrix operations, very highly efficient. This is what we need now for our racing problem. Here we have a so-called path transformer. It's a Dijkstra or the A-star, that you can apply on a graph that describes your racetrack from start to finish. And boy, you can really scale. A knowledge graph can start from a single neuron to a huge LLM that you use every day. The fabric is the same. We are talking about neural networks with nodes and edges and weights that are trained with data. This is nothing new to you, but I want to show you how we can apply it on our racetrack. So we can also finally scale to our race problem, where we generate on every place on our racetrack will be a node with a status of a speed and a speed at a position. And I'll show you now how we can use the traditional physics and combine with the data science. 10 minutes left. So, start line, finish line. This is the distance that we travel. This is one dimension of our graph. The graph that has nodes and edges. In the vertical we have the speed, all the possible speeds that the vehicle can cover. So let's say we kind of discretize space and time. Here we have maybe 100 meter steps, 50 meter steps, or 5 kilometers per hour steps in the vertical. And this is our graph. These are all possible speeds at all possible locations on the track. You see, we are now we go completely new way of describing a mathematical model. Then of course we have some nodes that are not valid. Let's say in a corner, you're not allowed to go in with like 45 km per hour. So you say, based on your vehicle, I have to limit, because of the coefficient of friction, centroid and so forth, I have to limit it to 25. This is where safety comes into the picture. So you have an upper kind of envelope that you cannot exceed, and you have a lower envelope that you also cannot go below. This leaves you with the nodes that are valid from start to finish. Here we have covered safety. And now we look at how can we combine speed and energy use. So we move now from PowerPoint to Python. And there is also QR code, Python code on the link that I showed you. You just scroll down, go to sandbox number 2. We will not have time now to go through this sandbox, but it's kind of easy to follow. Sandbox number 2 shows you how we create such a graph. So finally, the edges. If we, here are the positions x2, x3, 50 meters. If you have to overcome this, it resembles a neural network. You transition from this node to this node, and now we have to calculate the cost of this node, of this transition. So you can imagine that here, kind of, we have a maximum acceleration we are not able to exceed. Here we have a maximum, and that's why we cut it out. Here we have heavy braking. That is maybe also, we don't want to have too much heavy braking. That's why we also kind of cancel these two nodes. So this leaves us with nodes where we see this will be a burn. So we go from this state to the next. We have to accelerate. This will be a coast, and this will be braking. So this means these edges and nodes represent exactly what your driver is doing on track. Burning, coasting, hopefully not braking. And this leaves us, how do we calculate the weight of this edge? Because you know, in traditional machine learning, deep learning, you use data to do that. We do it in a way where we really program this weight the way we want it. This means this edge is actually the cost to overcome a certain speed difference over a certain location difference. And this means we have, when we remember back, where we have seen the Pareto front, this is now that the Pareto front merges into this formula. On the left-hand side, we have a term where we say the cost in time times the weight of time. This was the 1-0 thing, where we were, in this case, we were up here, right? And in that case, we were down there. We were walking down the Pareto curve, and with this weight, you can control how you want to, how your outcome should be like. Should it be fast? Should it be energy efficient? Or something in between? And all this with a physical formula that is actually hidden in this energy term here. You overlay it, or you align it in this edge. If you have a new formula you want to apply, like wind coming in or rain having some restrictions, you just go back into these formulas and add it to the cost of the node. So finally we see we have the cost of time. If we have a high speed, delta S over delta V, this cost goes low. If we have like a high force to overcome, like a big mass, for example, or a rolling resistance in the tires, this cost will go up. So finally, what we have is, we have now a model where we described the problem of from start to finish with a graph with nodes and edges, from start to finish. And the clue is now to move through this graph and find the the cheapest way to do that, and this is where this algorithm like the Dijkstra, this graph transforms come into picture. In earlier times it was called the salesman problem, to go from A to B in a very, very efficient way. You cannot do that by yourself. You have algorithms that do that for you. So you can say, I want to have sport, I want to be fast. The algorithm returns this speed profile based on your vehicle with all the models that you had, will be the best speed profile for you on this specific track. A track that even includes, as you see in the background, even includes the elevation. You move to eco, you see the speed profile goes low. Or here, something in between. So this means actually with your knob in mind, you can change the behavior of your vehicle anytime you want on the track. Energy efficient, fast. So finally, what is in the edges is the meaning, the true meaning. So we see here the solution of our multi-goal problem. Every scenario is in this in this edge, like the straights, the slopes, the corners. It's the way you want to have the energy efficiency or the short lap times. It was you who defined the weight on each of those. And we have seen that on the track, teams who have used this technique, they gained improvements between 7 and 25%. Not changing the vehicle, not changing the driver, just by using the right speed profile, the right strategy. But you've seen we started very low from getting the telemetry data, then the meaning of like a speed profile, how should the data be consistent. You see, you need all these levels to go through. You cannot start with an advanced concept like this, so you should start very at the beginning and make sure that your driver can apply a strategy and then go one level and the next, step by step. And these are real measurements from the industry. So you see, this is not just an idea, it is implemented, it is used. And it's a completely different way of approaching a racing problem than you do in a traditional way. And this is again, for those who are late, the QR code that brings you to all the sandboxes. So when you open this sandbox here, it shows you in Python, clear Python, very easy to follow, how this graph is created, how we calculate the edges, and how we get it out of this physical formula like F equals mass times acceleration. So finally then we can combine it with telemetry data. We can also include weather data. So the more information you add to the graph, the smarter it becomes and the smarter your strategy will be. And then finally, I mean, we just have 1 minute left. The sky's the limit. You can use these things that I have seen in the off-track awards to go from there, but don't start with like an ADAS, like an advanced driver's supporting system. Start with the basics, with the understanding the data first and understanding what is a data strategy. And then finally, this is also a sandbox. We don't have time to go into this. I show you how we can use race data and train a neural network. So the input will be the two speeds from between the, you can see the grid that I show you, for example, to overcome from 25 kilometers per hour to 35. This will be in this vector, and the outcome will be the energy efficiency and time efficiency trained by race data. So we have done it with 4 attempts. And you will have the same, really the same structure. So instead of creating and modeling these edges, you have modeled it by the data using a neural network. And the example shows how you can use, like, you can increase the layers to add dimensions, or you can increase the neurons to make it wider, to find more patterns in your data. So this is finally use AI to do that. And we are not talking about LLM. We are talking about machine learning, deep learning, the basics. And we use actually an easy to use entry-level library, it's sklearn. But maybe if you are more advanced, you will move to PyTorch, for example. That is also very known in the community. So that's it, that would be sandbox number 3. It's on the same page. No time to go through this one again, but I think we almost managed to complete the 5 levels. My idea was to show you what is possible with data, starting with telemetry and go the ladder all the way up. And our intention is to build a community that is really becomes proficient in this level, and we do the journey together and even exchange ideas. So how do you think? Would you be part of this community?
Yes, of course.
All right. So then, this is now happening in Qatar. This is the first event in Shell Eco Marathon 26, and you say you will be part of it. Then we kick it off. Okay.
Yeah.
That was a great result. This is what I hoped. I got goosebumps now. Thank you so much for coming. I appreciated that you came. And if you have any questions, I'm always in the tech inspection area at the exit. And I will also go around and talk with you about the off-track award submissions that you provided. Time is a little bit limited, so if I'm not able to visit every team, though it's not personal, it's just a limited time. So thank you so much for coming. I hope it was fun. I hope it brings you forward. And I look forward to new data, so when data comes into action. Thank you.
Thank you.
Thank you.